Good morning to our friends from Europe. I'm very glad to welcome Professor Albert here and the speaker today, Professor Aurélien Manchon. Very nice to have you, Aurélien. Thank you so much for accepting our invitation. And also some months ago, Albert gave a fantastic lecture on the completion of 1 year of our webinar series. I'm really grateful to all the speakers who are very kind to support our event. So, yeah, good afternoon, friends from India and Asian countries. So today we will have the lecture by Professor Aurélien Manchon, who is actually very known person in this community, but nevertheless, I will give a very brief introduction. So, Aurélien Manchon is a professor of physics at Aix-Marseille University, at the Interdisciplinary Center for Nanoscience in Marseille, in France. That's called CINA. His research focuses on the field of theoretical spintronics and aims at identifying novel mechanisms that can be used to operate spin-based devices. His research interests spans from speed-orbit coupled transport to chiral magnetism, antiferromagnets, and ultra-fast spin dynamics. Aurélien Manchon graduated from the École Polytechnique Palazzo in France in 2004 and earned his PhD in physics in 2007 from University Joseph Fourier at CS FinTech Laboratory in France. After that, he went for a postdoctoral fellowship at University of Missouri in Columbia and University of Arizona in Tucson. In 2009, he became an assistant and later associate professor of material science and engineering at the King Abdullah University of Science and Technology, that's known as KAUST, in Saudi Arabia. And he joined the Aix-Marseille University in 2019. So with this brief introduction, I again welcome all of you to this seminar and also thank Aurélien on behalf of my team, my co-convener Dr. Rajba Singh, other members Pushpendra, Sakti, and Ajay, and so on. So it's really nice to have you. Just a small announcement that during the lecture, we don't take questions. So if you have any questions, kindly write in the chat box, or just say, I have a question, or raise your hand. And at the end of the lecture, we will take all the questions one by one. With this, thank you so much. And Aurélien, it's all yours. Please start your lecture. Thank you.
Well, thank you very much, Subankar, for the nice introduction and for the invitation. I'm actually very, it's really an honor to be online with you guys today. So I would like to maybe just give you a few heads up about this presentation. I understand that we have many students or young researchers online, so I will spend a bit more time on some pedagogical aspect of the Spinobit torque, and then I will explain how we can use Spinobit torque, or we say the specific characteristics of the Spinobit torque in certain materials, certain classes of interesting ferromagnets and antiferromagnets. Actually, Spinobit torque, and I would say most spinobitronics business is really the art of manipulating spin balls. So if you're from Europe, well, you probably know this particular game very well, which is the selection of the World Cup. It was in 1997 between France and Brazil, and you had this Roberto Carlos shooting this very impressive goal. And the way he did it he actually induced a very strong spinning motion to the ball, and the spin of the football coupled to the trajectory of the ball to bend it and to actually reach the goal. And this mechanism is of course very well known in classical mechanics, and it is called the Magnus Force. And this is typically what we're trying to do when we are exploiting Spinobit coupling, that we're trying to control and to design the Magnus Force exerted by the environment on the traveling electrons. So this example, but you have actually many other examples, and I was actually looking for one in cricket because we are in the cricket country, and you see this one is actually quite impressive. I don't know if you can follow the ball let me see this small black point here. And by inducing a very strong spinning of the ball, so rotation of the ball over itself, you can see that the player can actually trick this guy and the ball goes completely the other way around. Well, I'm not sure it's completely due to Magnus Force, because there's actually a connection between the the ball and the bat here. But anyway, so see that connection between orbital motion and spin motion. So this actually would look like skew scattering in spin Hall effect in a sense, right? When you basically just upon scattering, you have a change of motion of the ball. Okay, so this is the general frame, and this is a general physical effect that we're trying to exploit. You can, of course, this is not only restricted to football, soccer. There's actually a long list of balls that have been tested by these people here in ESPC in France. There's a full paper discussing the Magnus effect in sports. I really encourage you to have a look at this very original and instructive paper. So basically, the Magnus effect is happens when you have a spinning ball in a fluid. Okay, so imagine that there's a flow of air or flow of water going, let's say, from right to left, and you have a spinning ball here. So you see that in this particular case, the ball is spinning clockwise, which means that the velocity of the fluid on the top with respect to the ball is much faster than the velocity of the fluid with respect to the ball at the bottom here. So you can have a difference of pressure because of this different velocity or relative velocity, which translates in a force, a transverse force that will actually push the ball on the side. So this is the Magnus effect. And if you want to cancel the Magnus effect, you need to make the ball spin along its trajectory, along the flow of fluid. And this is what we do if you play American football, for example, or rugby, and you want to, you have this oval ball, and if you want to throw the ball very, very far, then you have to make it spin around its trajectory. You can also use this effect to make boats. So I think this is the modern version of this boat. You can also try to use it to make planes. And as I understand, the plane actually didn't really work, but the boats actually do work. So you still have those boats with this very big chimneys here, this very big cylinder that actually rotates and drag the boat along the wind. So you can have more information by just looking at this paper, at these two books here. So now, how does this Magnus force translate at the level of the electron? So we know that electrons, like many particles, are characterized by their momentum P. And if you actually throw a moving electron in an electric field, well, this electron will experience a magnetic field in its frame of motion. Okay, this is just simple relativity. Now, because this electron on top of that has this spinning motion, the magnetic moment of the electron will couple to this magnetic field. You will end up with a Zeeman term that is directly proportional to the momentum of the electron. So that is characterized by this spin-orbit Hamiltonian, where sigma here is the spin of the electron. The gradient of V is the potential gradient. So this is simply the electric field felt by the electron. And P is its momentum. Okay, so this is actually a very general coupling between electron's momentum and its own spin that is mediated by its environment. Okay, so the potential gradient plays the role of the moving fluid, if you wish. Well, when an electron flows or travels close to an ion, the potential is mainly central. So the potential gradient here is actually mainly radial, which means that well, the magnetic field that is experienced by the electron is rather, let's say, r cross p in this direction here, which means that you can rewrite this Spinobit coupling interaction, this is the general form here, into the very famous sigma dot L, where L here is r cross p, the orbital moment of the electron. And now you can see directly that there is a coupling between the orbital angular momentum and the spin angular momentum. Now the question is what happens in crystals, because in crystals you have an infinite repetition of the central potentials. So of course there is always a bit of a deviation from the central potential, but if you look at the gradient is dominated by this radial form here. So in crystal, if you project the Spinobit coupling on the Bloch states of the traveling electrons, you can rewrite it in this form. So it's essentially a Zeeman term between the spin and something, and you can actually project this part on the orbital part of the Bloch states, and you end up with an effective magnetic field that will be K dependent. So K here is the crystal momentum. So depending on the symmetry of the system, you can actually have various forms of this effective field. So if you have inversion symmetry, which means that you can map BK to B minus K. Okay, so those two effective magnetic fields are equivalent depending whether you go, let's say, one way or the opposite way. Okay, you have this symmetry here, and if you have this symmetry, well, the effective magnetic field is 0, but it creates what we call an anomalous velocity through the Berry curvature. So this is probably something you have heard already. So I'm not going to enter into the details of the Berry physics. It is, of course, present everywhere when we talk about spinobit transports, anomalous Hall effect, Johnson-Skimmer interaction, spinobit torque, but I will not spend too much time on that today. So if you have inversion symmetry, the velocity, the spin-dependent velocity of your carrier will have, well, this very, the canonical velocity here, just a derivative of the dispersion with respect to the momentum, plus a correction or a contribution that is directly proportional to the Berry curvature here, and S being the spin projection. So depending when you have spin up or spin down, you will go either one way or the other way. So this anomalous velocity is going to separate the spin up and the spin down and will create a transverse pure spin Hall current. So that's an important consequence, and we're going to see that we can actually use that to torque magnetic materials. Now, if you have inversion symmetry breaking, so there is no center of inversion, sorry, in the crystal. So it could be a non-central symmetric crystal, it could be an interface. Then this magnetic field here is not even in momentum. Okay, it could be odd, or it could be well, both odd and even. I would say, you can just develop it in terms of the powers of the momentum. And in this case, the odd part, the part that is the magnetic field that is odd in momentum, will create what we call an inverse Spingavanic effect. So the way it happens is that if you take an interface, for example, if you take an interface, so I will give you the wrong picture, but the picture that is, it's working from the symmetry perspective, but it's not quite the macroscopic physics. But anyway, so if you have an interface, then you could say that on top of the central potential coming from the ions, you also have a gradient of potential that is perpendicular to the interface. So if you say that the interface is normal to the z direction, in this case, you can replace this gradient here by a number, something that looks like that. Let's say some derivative carried by the vector z, and then you end up with a sigma dot z cross p with some coefficient here, and you end up with this effective spinobit Hamiltonian. The spinobit is known as the Rajba or Rajba-Bishkov-Vasko spinobit coupling. So let's call it Rajba spinobit coupling to make it simple. And what you see that this is linear in momentum. So it's a Zeeman term where the Zeeman field is simply proportional to the momentum of the electron. So it means that if you send a current along one particular direction, so the average, statistically average momentum is non-zero anymore, in this case, the spin of the electron will experience an effective magnetic field, and it will tend to align on this effective magnetic field. So this is exactly, this picture that I was showing previously. It's taking some time, sorry for that. Here, where the player induces a rotation of the ball along the trajectory to cancel the Magnus Force. So that's essentially what you have at interfaces, except that now you have inversion symmetry breaking. So the symmetry actually imposes the spin to rotate in one particular direction. Now, if you look at the symmetry of this Hamiltonian here, the spin cannot be along the trajectory. It actually has to be perpendicular to it. Okay, this is the specific Rajba orientation. So now the question is, how can we use those two effects, spin Hall effect that creates a pure spin current, and inverse spin galvanic effect that creates out of equilibrium magnetization, out of equilibrium spin density, how we can use those two effects to create a torque on an adjacent ferromagnet. So let's look at how the spin Hall effect works. So this effect works in crystals, so non-magnetic crystals that have that can have or may not have inversion symmetry. So if I just take platinum, for example, inversion symmetric, and I deposit a ferromagnet on top of it, let's say cobalt here, and I send a current through my system, then inside the platinum, inside the heavy metal here, I will have the separation between upspin and downspin, which means that I will create a spin current, just do it again, that will be absorbed by the ferromagnet, and that will exert a torque on it. Now, if you look at, with the hands at the microscopic physics, what's happening from the magnetic material standpoint is that this magnetic material absorbs a spin current. And by absorbing this spin current that has been generated by spin Hall effect from this layer here, it will experience what we call a damping torque. So it's a torque that is even in the magnetization direction. And if you look at the symmetries, you end up with something like that, with a Z cross J here that is imposed by the specific geometry of the structure. So that's one mechanism. Now, if you take the other mechanism, the Rajba effect, what I call the inverse Spingavanic effect. So we have this Rajba Hamiltonian here. There's only present when you have inversion symmetry breaking. So typically at this interface here. And in this case, if you look at the very, let's take a very simple model. It's just a two-band system where this term here induces a spin splitting. Okay, so you're going to have those two bands here crossing at this point. And if you cut, so this is the kx and this is the energy here. If you cut in the at one particular energy, the iso energy curve are given here. So you're going to have one band structure, one surface, one Fermi surface with one chirality, and one Fermi surface with the other chirality. So the small arrow here is the spin of the carrier, and this particular point here is a point in k-space. Okay, so if I take this point here, it means that an electron that is flowing along this direction here will have automatically a spin perpendicularly to the direction of propagation. And this is what's happening at every single point here. So that's at equilibrium. Now, if I inject an electric field in the system, I'm going to depopulate electrons with negative K. I'm going to populate states with positive K. Okay, so I'm going to essentially shift, if you wish, the Fermi surface. I mean, that's a picture. You're going to shift the Fermi surface and create more states with positive K than with negative Ks. And what you see that this state with positive K will create a non-equilibrium spin density along this particular direction here, okay, perpendicular to the electric field. So you end up with a spin density. It's not a spin current, okay, it's a spin density. So it's a magnetization, if you wish, that is proportional to Z cross the current. So you see you are kind of the same symmetry here, huh? Z cross J, for different reasons, in a sense. You have the same symmetry. So in one case, you create a spin current, so you really transport spin information. In the other case, you create a spin density. So you create out of equilibrium a spin density at a particular point of your material. So what we proposed along other theories, and I have to say that Andrei Bernevich and Alan MacDonald already proposed this idea at about the same time. The idea that you can actually use this non-equilibrium spin density to torque an adjacent magnetization. So this is what we proposed a long time ago, where we have the two-dimensional magnetic ferromagnets. Of course, when it actually works now. You have an insulator here, and at this interface right here, you have Rajba Spinobit Coupling. So if you send a current this way, you're going to create a non-equilibrium spin density that can torque the magnetization. And because it's a density, it's a spin density, then the torque will be like a field. This is what we call the field-like torque. You see, the torque is simply the magnetization, M, cross the spin density, okay, with some energy coefficient here, which I will not mention. This is just the SD exchange energy. Okay, so you see that those two different effects creates, in principle, two different torques. Spin Hall effect gives you damping torque, and Rajba effect gives you field-like torque. So that is a very, I would say, the simplest idea, or the simplest way you can look at spin-orbit torque. And of course, now we know that that things are actually much more complicated. So this spin-orbit torque has been studied in many different kind of materials. So as I said, magnetic metal heterostructures, when you have, let's say, platinum, tantalum, and tungsten, and so on. You can also put some topological insulators below here. And on top, you put some ferromagnets. You can also put insulating ferromagnets, YIG, thulium garnets also. It has also been observed in non-central symmetric magnets, so bulk magnets that lack center of symmetry, center of inversion. It has also been extended to antiferromagnets, and I think even recently to non-coherent antiferromagnets. I'm not completely sure about that. Yes, it was, yes, but okay. Now, once you have that, what can you do? Well, you can actually create, I mean, you can generate from that many different classes of devices, like the magnetic memories, nano oscillators, racetrack memories, interconnect spin logics, and so on. So I will not talk about that today. I'm just going to talk about the nature of the spin-orbit torque in some selected samples. So before we move on, I think it's important that we actually ask ourselves what is the microscopic origin of the Rajba effect, because everywhere you observe spin-orbit torque, you need to break inversion symmetry. So usually Rajba effect and spin Hall effect are companion effects. They are usually present together, especially when you look at spin-orbit torque and spin-to-charge conversion effect. So one way to look at it is to develop a simple time-bending model. So I will go a little bit in the depth of this model because we have students in the audience, and I think this can be always instructive to know how we can build a simple time-bending models. And I'm going to introduce orbitals, because actually orbitals hold the key for understanding the microscopic physics of those effects. So I'm going to take a chain, and I'm going to put a PZ orbital, okay, perpendicular here, and a PX orbital. Okay, so I just have this chain here. So of course I have inversion symmetry, and PX and PZ orbital do not mix with each other. To induce inversion symmetry breaking, I'm going to add another chain on top, okay, which could have, let's say, different on-site energy, different hoppings, and so on. I can tune the way I want, and I'm going to assume, just for simplicity, that this chain only has PZ orbitals. I could also put PX, but my Hamiltonian would be larger, would be more difficult to get analytical formula. So I'm just going to take a PZ orbital on top here. And what you can see is that in the absence of this symmetry breaking, my PZ and PX of the bottom orbital, that's the one I really care about, do not mix with each other. But once I break inversion symmetry here, I'm going to mix them. Okay, I can mix PZ and PX through the top PZ orbital here. And this mixture will, so the coherent mixing between PX and PZ will give rise to an orbital momentum, Ly. I didn't talk about Spinobit coupling yet. Okay, there is no Spinobit coupling in this picture. It's only a matter of orbitals. So I can create my very simple 3x3 Hamiltonians where I have, let's say, the on-site energy for the top orbitals, and I have the two on-site energy for the PX and PZ orbitals for my bottom chain. Just for simplicity, I'm going to say that they are the same, which is not the case in principle, but that's fine. It's just for the sake of the demonstration. And I have some hopping parameter that couple, let's say, PX with PZ, that's this one, and PZ bottom with PZ top. Okay, this is the VZZ coefficient here. I can use Slater-Coaster parametrization. because remember I have block states here, and because I have block states, the VZZ will be even in Kx, and the VZX will be odd in Kx. So I really invite you to have a look at the Slater-Coster paper that gives you all those coefficients, explain you how you can get it. And that's actually the key here. You see that the coupling between the mixture between Px bottom and Pz top is actually odd in momentum K. So if I go, let's say, from the left to the right, this coefficient here will be positive, but if I go from the right to the left, it's going to be negative. So that's the only place where this guy changes sign. Okay, let's move on. So I can diagonalize my Hamiltonian, get my eigenstates, and I'm just going to look at one of them, okay, just for the sake of simplicity. If I take this particular state here, I see that I'm going to have a mixture between the Px and the Pz orbital of the bottom chain. You see that now my states is a superposition of Px and Pz, which only appears because I put a chain on top here. Okay, this mixture is coming because is arising in my equation because I turn on the mixing between the Px and Pz. So it means that because I have both Px and Pz, I should have an orbital momentum. So I can calculate this orbital moment of this particular state, and I see that it is of course along the y direction. Okay, when I mix Px and Pz, I'm going to obtain an Ly. And if I explicitly write this expression, I see that this orbital moment is in fact odd in momentum K, which means that if I send a current from the, let's say along the positive, if I send carriers along the positive X, then those carriers will acquire an orbital moment. They will actually start rotating. So they actually do not move on in a straight line. They actually move on this way, okay, like a cycloid. And again, this is without Spinobit coupling. So that's actually the key, in my mind, of Rajba Spinobit coupling, especially in transition metal interfaces and other complex multi-orbital systems. Now, if I turn on Spinobit coupling, what happens? As I said, the Spinobit coupling is mostly an atomic Spinobit coupling. So it's mostly given by L.S. So you see that if I create an Ly, then the spin of my electron will also tend to align along the y direction because of Spinobit coupling. And that's exactly what I have here, okay? Because I have Px and Pz, then the spin will try to align along y. If I extend the model to 2 dimension, I'm going to have also, let's say, Px, Py, Pz. I'm going to have in-plane Rajba effect. Of course, I can also extend it to the d orbital, but this is much more complicated. But this is working exactly the same way. So the take-home message is that it's really the combination of Spinobit coupling and symmetry breaking that generates the spin texture in momentum space. And the spin texture is coming from the orbital texture. And the orbital texture is really a substructure of the spin texture. I exemplified this idea on a much more complex system. So we took this, I would say, I put some quotation marks here because it's a fake iron tungsten, because we just a few, let's say only the d orbital, the iron tungsten, and we impose some hopping parameters. So we have this bilayer here with the 5 monolayers of iron on 7 monolayers of tungsten. And if I get the, if I look at the band structure, I get this spaghetti, very complex spaghetti band structure. I can try to see if I can get some information about the orbitals. I can project these bands on the different orbitals. You see, it's a real net. It's very hard to identify any information here. But now, if I look at the orbital projection, then you see that I'm going to have Lx, Ly, Lz. So Lz actually doesn't have any particular symmetry. It's actually it has inversion symmetry along the in the Kx Ky plane. But if you look at the Lx along the Ky plane, so this is from minus Ky to plus Ky, then you see that I'm going from the blue curve, from the blue color, which is -1, to the red color +1. So it's really anti-symmetric. And if I look around what's happening around the minus Kx plus Ks direction, I'm going to have an Ly that is also anti-symmetric. So I have a Rajba effect, but for the orbital moment. Now, if I turn on Spinobit coupling, I'm going to imprint this orbital texture on the spin texture. And again, I'm going to see that the SX component is anti-symmetric along the KY line, and the SY spin text, the S1 spin moment is also anti-symmetric along the KX line. Okay, I think this is a very important aspect of the Spinobit coupling. So of the Rajba effect, that you really have an orbital Rajba effect that is a substructure of the spin Rajba effect. Of course, okay, that's just, I will go fast on this one. So it means that if I go back to my chain here, I send a current in this direction, I'm going to create a non-equilibrium orbital moment. And because I have Spinobit coupling, I will end up with my Rajba effect. And this is something you can really observe. This is the first observation of the Rajba splitting at the surface of gold, 111. Okay, you can have more information by looking at those reviews here. So now what I want to do is to see what's happening in a real structure. Okay, I want to develop modeling calculations to model realistic, or as realistic as possible, heterostructures, and try to understand how Rajba effect, spin Hall effect, and possibly other effects can contribute to the spin orbit torque. So typically what I have is a substrate that can be a transition metal, usually heavy metal. It could also be a topological insulator, well-semi metal, whatever we want. And on top, we're gonna deposit a ferromagnet. So if I send a current, let's say in this system, I'm gonna have electrons flowing close to the surface. That will generate the inverse Spingavanic effect. That's what I'm expecting. I'm going to also have, So this inverse Spingavanic effect should create the field-like torque. Okay, just this, I can just put whatever I want on top. Let's say ferromagnet, cobalt, iron, nickel, yig, iron, germanium, tellurium, whatever you want. And that will create that this inverse Spingavanic effect here should create at least dominantly a field-like torque. And the bulk flow should create spin Hall effect that create a damping-like torque. Well, for the past 10 years now, a bit more than 10 years, we have been searching all kind of material systems and transport regimes and situations. And we have actually realized that this very simple idea that, spin Hall effect create damping torque, so this kind of torque, and inverse Spingavanic effect, Rajba effect, if you wish, create the field-like torque. This simple idea is not completely correct. It can be correct in certain situation, in the simplest situation, but usually when you have a system that is a very thin, ferromagnet and very thin substrate, things are much more complicated. And we can actually list many different effects. We have found, for example, that the Rajba effect creates not only field-like torque, but also damping-like torque. Then in certain situations, the spin current generated by the spin Hall effect creates not only damping torque, but also field-like torque. And that many actually other forms of torques with complex angular dependencies can exist in those systems. So I will not enter in all those details because this is actually a fairly complex and I would say quite specific to the system under study, but I will try to give you some insight about how things work in at least 3 or 4 selected systems. So I will start with the simplest one, which is the transition metal heterostructure. So the system I'm considering is this this bilayer where I have actually a BCC crystal here. And so you have a BCC non-magnetic metal, and on top of it, I just deposit another BCC ferromagnet. I'm going to represent this guy by this sort of Hamiltonian, where I have the Hamiltonian of the monolayer. So this is each monolayer is represented by this time-binding model with, let's say, 10 orbitals. I have exchange. I have atomic Spinobit coupling. And what I'm going to do now is that once I have this Hamiltonian for one specific monolayer, I'm going to just tag them. Okay, I'm just going to pile all those monolayers on top of each other, create a very big matrix, and that will create my supercell. Once I have my supercell, I can get the Green's function, and I can use all the tools that I have learned from quantum transport. So in this particular case, we actually take only the 10d orbitals of iron and tungsten. We impose that iron has the same lattice parameters as tungsten, which is completely wrong. But at least I will have a system that is a compromise between the simplistic free electron model and the super complicated and as accurate as possible DFT calculations. Okay, I really try to find a compromise, something I can calculate and manipulate. So, well, I can get my density of the density of states for iron and tungsten. So this is the one I can get with my time bending model. This is the one I should get with realistic density functional theory calculation. And you see that, of course, is different, but it's not too bad. I can get my band structure. So you already have seen this one where I can see the anti-symmetric spin density that is giving me the Rajba effect. I can also have magnetism and so on. So let me spare you with that. And what I'm interested in is, of course, to compute the spin density that I will generate when I will send a current along the plane of this bilayer. So you have here the non-equilibrium spin density. Let's look at the black curve when Spinobit coupling is present in the iron layer here and in the tungsten layer. Okay, remember this is a fake iron, a fake tungsten, but still I would say it's good enough to understand a bit what's going on in a standard transition metal heterostructure. So if I look at the SY component, let's look at the SY component. First, you see that I have a lot of density right at the interface and almost nothing in the bulk here. And again, a lot of density at the other interface. So this is the Rajba effect. And what I like with this kind of picture is that it's a Rajba effect that is coming from the atomic Spinobit coupling. Okay, this is really similar to the picture I gave you previously. This Rajba effect is coming from the orbital mixing at the interface. So that is fine. So this one should give us some field-like torque. And if I look at the SX component, you see that things are actually a bit more interesting. So the SX trace rather deep into the ferromagnetic, so it's far away from the interface here, which is really a signature that this is not a purely interfacial effect, but it's really coming from the buildup of the spin density inside the heavy metal, which means that this is rather dominated by spin hole-like effect. I say spin hole-like because, of course, we are not in the diffusive regime. We are something that is close to diffusive regime and not completely diffusive. So you can really see that the SX and SY components, this one giving the damping-like torque and this one the field-like torque, already have a different characteristic. One is really interfacial. This one actually extends in the bulk of the heavy metal. We can also look at the dependence of those two effects with the disorder. So if I look at this field-like torque, I'm going to have 1 over gamma. So gamma is my disorder broadening, 1 over gamma behavior, which is the same you would have for conductivity, for example. Okay, so the field-like torque behaves like the conductivity. So this is what we call an extrinsic effect. While the damping-like torque has a completely different behavior. And you see that actually if I take gamma, so my disorder to 0, it doesn't diverge. Field-like torque diverges, but the damping-like torque actually saturates. So this really means that this guy is what we call an extrinsic effect. This is more like a Boltzmann effect. While this one is intrinsic, it's connected to a Berry curvature. It survives in the absence of disorder. Well, we can also do something that is pretty hard to do with full orbital DFT calculation, that we can really change the thickness of the layers and see how things are changing. So if I change the thickness, let's say this is the thickness of the normal metal, you see that the damping torque, the field-like torque, sorry, is essentially flat. Okay, this is for different disorder. It's essentially flat, except at very, very small thicknesses because of quantum resonance, which really means that what we have is something that is purely interfacial, or mostly interfacial, I would say, above 20 model layers. Now, if you look at the damping torque, it's interesting because it actually changes sign. So for very, very small thicknesses, the damping torque is negative, and for large thicknesses, it's actually positive. So what the way we can interpret these behaviors at very small thicknesses, you don't have spin Hall effect yet, because you cannot build the spin currents inside the normal metal. So what you have is an interfacial effect. it's really coming from the combination between Rajba effect plus magnetism. This is an effect that we call Magnetoelectric effect. And this is connected to the Berry curvature of an interface in the presence of magnetism. Now, if you increase the thickness of the heavy metal, then you change the sign and you get some positive sign. And this is because now spin Hall dominates, because then you can build a spin current inside the ferromagnet because it's thick enough, and then you can change the sign. The fact that the interfacial contribution and the spin Hall contribution are opposite in sign, I think is mostly accidental. Okay, this is not something we have studied in depth, and I think it probably deserves more investigation. But I would tend to believe it's more related to the specific parameters that we have chosen. Okay, I will not talk too much about the thickness dependence of the ferromagnet because this one is kind of standard. You basically saturate rather quickly because in this region here of very small thicknesses, you have what we call spin dephasing. And when the thickness of the ferromagnet is big enough, then you have dephased all the spin that was perpendicular to the magnetization. Okay, I will not talk about the angular dependence because I'd like to move on to more funny materials. But of course, we do have angular dependencies, which can be actually very, very strong. So the very simple picture that we have M cross Z cross E and M cross Z cross E cross M, this, feed-like torque and damping torque, is not sufficient. So when you analyze experimental data, you should be very, very careful that those feed-like torque and damping-like torque are usually not sufficient. And in real life, in real samples, you actually do have very strong deviations from those simple torques. Now I'm going to move on to another system that is the L11 compound, system that has been grown by my collaborator Jingchen Cheng in NUS. So his group has expertise in growing perpendicular materials, very, very neat perpendicular materials. And what they looked at was this bilayer, this copper platinum and cobalt platinum bilayer with L11 crystal symmetry. This L1 crystal symmetry is interesting that what they observe is that they can switch the magnetization of the system, but it depends on the relative orientation. Sorry? Excuse me? Okay.
I think there was somebody speaking, I muted him, so please continue.
Okay. So what you can observe is that you can switch the magnetization using Spinobit torque, but this switching will depend on the relative orientation of the current with respect to the symmetries of your system. Okay, so the symmetry axis, of your crystal. So if you, let's say, if you send the current along 1, -1, 0, then you have this nice switching behavior. If you send it along this particular line here, which is a high symmetry line, you see that along this direction, those two atoms are symmetric with respect to each other. Okay, if you send it here, then you cannot switch anymore. Then you send it along the 60-degree around here, then again you can switch, and so on and so forth. So you have this very strange oscillation of the switching behavior of the system. And if you actually look at the point group of this material has this 3M point group, which means that we have a threefold rotation plus a mirror symmetry. And you can actually, and this is detailed in this paper here, you can actually use those point symmetry to extract the form that the torque should adopt. And what you obtain is that you have those, let me see, the torque should have this damping-like behavior. That's fine. We know that it's not very surprising because there is inversion symmetry breaking. You should also have this fig-like torque here with some Zim component, but that's again not very surprising. This is just an isotropic damping torque, if you wish. But what is mostly interesting is that you have this new torque here that has a very interesting behavior. You see, it's a torque that vanishes if the magnetization is perpendicular to the plane, and that is maximum if this is in the plane. And it's actually not only present in those L11 crystals, it's also present in iron 3, germanium, thorium 2, and other two-dimensional magnets. So let's look at how things work and how we can understand the experimental behavior. So if you send a current, let's say along the -1, -1, 2 direction here, Well, the first thing that is going to happen is that you're going to have the damping torque. Okay, the what we call the 3m torque here is not active because magnetization is perpendicular. So this one brings the magnetization in the plane. Okay, the damping torque brings the magnetization in the plane, and once it's in the plane, then this torque, the 3m torque, becomes active. So if you send a current along, let's say, this particular direction here, once the magnetization is in the plane here, the torque you're going to have would be minus m cross x. So it actually brings the magnetization back to its original position, so no switching. Now, if you send the current along this direction here, let's say the 30 degrees, okay? 30 degrees, what's going to happen is that you will still have the damping torque bringing the magnetization here, but then the torque is 0. The 3m torque again is 0, so nothing happens. What is interesting is that if you send it along 60 degree, I mean, based on my, on this notation here, then the damping torque will bring the magnetization in the plane along this particular direction here. And along this direction, the 3m torque is not minus m cross x, but plus m cross x. So in this case, the 3m torque will bring the magnetization on the other side. And now you have switching. So you can, just do some very simple calculations and try to map the behavior of the switching behavior of the system. And you can indeed see that for specific direction of the current, you're going to have some nice switching behavior. And for other specific direction, there's no switching behavior. Again, as I said, this is something you can find in iron 3, germanium, thorium 2. Okay. If you actually analyze the symmetry, you find that you have the same torque. And this is something that was observed by Bratta's group in 2019. What is interesting in this system that there is no damping torque though, because you have a very strong mirror symmetry that actually killed the damping torque. So the only torque you have is this one. So you cannot switch, but you have what we call current-driven anisotropy. So I will not talk too much about that. I see that time is running, so another 5 minutes if I'm allowed to present shortly what we have done in other materials. We also spend some time trying to understand what's happening with the 2D magnets. So I'm sure you have heard the presentation of Albert on these 2-dimensional magnets, which is really attracting a lot of excitation. In this presentation, I'm going to focus on vanadium diselenide. And what we are trying to do was to break the inversion symmetry of those chalcogen, the transition metal dichalcogenide, by differentiating the top chalcogenide from the bottom chalcogenide. So this is something that's been done experimentally for MOS2, when you can basically change the sulfur with selenium. You can go this way. And if you do that, you're going to create inversion symmetry breaking, and you're going to create a polar material where you're going to see a nice Rajba Spinobit coupling in this system appearing. So we have done that with vanadium dichalcogenide. Here is the example of what we have. We have selenium here, tellurium here, and vanadium. So you should have some Rajba Spinobit coupling. We have performed a systematic investigation of the magnetic properties. I will not talk about that too much. What's happening is that when you increase the electronegativity of your chalcogen elements, actually distort the orbitals and distort and change the charge transfer between vanadium and the chalcogen elements. Now, if you have different chalcogen elements, then of course you're gonna have a different. Well, I would say most of the electron will go from vanadium to selenium, not to tellurium. And in this case, you're going to have this distortion of the orbital. And you see that the orbital here is actually asymmetric, which here it's actually symmetric. And this one will create a Rajba effect. So you can look at the Rajba spin texture. This is what we can get here, this nice anti-symmetric spin texture. That's what's happening for the selenium atom, for the tellurium atom. But what we care is about the vanadium atom, because the vanadium atom is the one that is magnetic. So it's the one that you want to imprint the Rajba Spinobit coupling on. Of course, if you change the couples here, sulfur selenium, sulfur tellurium, selenium tellurium, you have an increase of this Rajba Spinobit coupling. So we can focus on vanadium selenium tellurium, where you have the strongest electric polarization and then the strongest Rajba Spinobit coupling. have developed some small model, but this is already something that we have talked about previously. So I don't want to talk about that too much today. And what we can get in principle is a Spinobit torque. So let's now move on to the Spinobit torque investigation. So from the symmetry perspective, we have 3-fold rotation plus mirror symmetry breaking. We should have something very similar to this L11 crystal that I talked to that I talked about 5 minutes ago. So we should have the field-like torque, the damping torque, some anisotropic damping torque, and this 3M torque I mentioned. So this is what symmetry tells us. Now, we partnered with Jose Garcia and Stefan Roche in ICN2, and they performed some very nice quantum transport calculation using the density functional theory results that we got. And what they obtained was that they do observe indeed field-like torque and damping-like torque. You see the efficiency is not fantastic. It's a few percent. What I is that of vanadium, which is 20 times and even more smaller than platinum. So platinum, just to give you an idea, gives you an efficiency of 8%, 10%. Our vanadium system gives an efficiency of 2%. Of course, it's smaller, but it is actually quite large if you consider the smallness of the Spinobit coupling. Now, what is quite interesting is that we do not observe this strange the 3M torque here, which is a pity because the 3M torque here would allow us to obtain field-free switching. We do not observe it because to observe such a torque, you need the block state. I mean, that's my understanding, that you need a block state to experience the specific symmetry of the crystal. And this is something that is that is very hard to obtain when the transport is dominated by the gamma point. And this is our case here. Transport is dominated by the gamma points. So we're going to have only the easiest symmetry, not the complex ones. Okay. Well, if I have a couple of minutes left, I will like to move on to the last topic I would like to cover today, which is the Spinobit torque in collinear antiferromagnets. I'm not going to talk about non-collinear ones. So antiferromagnets are super exciting. There have been a lot of experiments recently on various aspects. The one I'm going to focus on is either Spinobit torque. The reason that they are exciting is that if you look at the excitation of the antiferromagnets, the excitations are usually on the terahertz range rather than on the gigahertz range. So if you can control antiferromagnets, you can pump them, then you should be able in principle to obtain terahertz excitation that are controlled electrically. So this is something that has attracted a lot of attention in the past few years. The question is, how do we torque an antiferromagnet? And here I'm really using the picture that that came out of Thomas Jungwirth's mind, I'd say. So if you take two antiferronically coupled sublattices and try and just apply a magnetic field along, let's say, this direction here, what you obtain is just a canting. So nothing really interesting. You cannot really switch it. So it's going to be a spin flop transition. Now you could say, okay, I'm going to try to apply it perpendicularly. Well, if you do that, again, spin flip. Okay. So you're going to progressively align those two spins along the magnetic field, but you're not going to switch it. So the idea is actually to find a way to create a staggered field. So a field that has an opposite sign on the two sublattices, which is kind of crazy. And what is actually quite amazing is that if you can create this staggered field, then you can switch the antiferromagnets pretty much like you would do with a ferromagnet. Now the question is, how do we do that? And that was really the discovery of Thomas Jungwirth's team and Jairo Sinova, that this is actually happening in this manganese to gold or copper manganese arsenide, which is a system where if you look at the crystal structure itself, it has inversion symmetry. But if you look at the sublattices, the two sublattices here, they both experience inversion symmetry breaking with opposite polarity. Okay, so if you send a current here, this guy is going to experience a Rajba torque. You see, you have, let's say, from this perspective here, from the red plane perspective, you have a gold atom here and a manganese atom here. From the purple layer perspective, the gold atom is on top and the manganese atom is on the bottom. So they will experience Rajba with opposite sign, which is exactly the staggered torque, the staggered field I was talking about. So then you can actually switch the magnetization. So I really encourage you guys to have a look at those very nice papers. I also propose a theory where we can now use spin Hall effect. Okay, so exactly the same idea, but now you inject it on an antiferromagnet. And when you compute that, you can find that you have a damping torque, exactly like the one you would have in a ferromagnet. And indeed, you can torque collinear antiferromagnet with the damping torque, because the damping torque would do the same thing as a staggered field torque. Now, this is the last slide of this already long presentation, where just to exemplify the power of the staggered field and damping torque compared to a magnetic field, I take a biaxial antiferromagnet. These are just simple LLG simulations. You can just do that very easily yourself. I take a biaxial antiferromagnet. So I just have two sublattices with two anisotropy directions. So you have this easy axis here and this easy axis here along. So one easy axis along Y, one easy axis along X. So I start with Y, and what I want to do is to switch it to have this order along X. Okay, so this is my exchange, a very large exchange, which is just usual for antiferromagnets, and a reasonable anisotropy, so biaxial anisotropy. So of course, if I apply a magnetic field along the X direction, well, then I'm just going to cant my magnetization. Nothing interesting is going to happen. The only way I can switch the antiferromagnet from here to there is either to apply a staggered field, and in this case, it works actually very well. I can actually use a very, very small staggered field, okay, like 0.001 Tesla. Why? Well, because when I apply a field, remember, this is exactly what is, similar to what happens in fairly similar to what happens in a ferromagnet. I'm not going to compete with the anisotropy. I'm going to compete with the anisotropy and the damping. So actually, I just need a very small staggered field to switch my antiferromagnet. I can also use a damping like torque. So M cross X. So with a polarization along X. And again, I can actually switch my magnetization. This is this red line here. Okay, I go from 0 to -1, -2 in this case. So I'm going to align on X. And in this case, again, I can use a fairly small torque. So it looks like it's a little bit larger than the staggered torque, but basically damping torque and staggered torque can do the job. So you can either use spin Hall effect or intrinsic Rajba effect, for example. So with that, I'd like to thank the guys who actually did the work that I presented today. And thank you very much for your attention. I would be very happy to start the discussion.
Okay, thank you so much, Aurélien, for this wonderful overview of really many things. You have done a fantastic job in addressing both the students as well as the experienced researchers. So it was really a pleasure to listen everything. So before we take the questions, I like to request everyone, if possible, to just switch on your videos, and we'll take a group photo. And Aurélien, could you just stop for a second your sharing screen so that, yeah. Okay, now we have everyone. But how do I put this gallery view? All right, here we go. Yeah, so still many people have not switched on. If it is not not a problem, so please. So I take a screenshot now. Okay. So ready, 1, 2, 3, smile. I have to take more. So, okay. There are still more people, so I can take only. So there are 3 windows. So ready. Yeah. Thank you. Great, very nice. Thank you so much for your kind cooperation. So now I think, Aurélien, you can again start sharing your screen and we take questions. Thank you so much. So we can switch off our cameras. So I don't see any questions in the chat box. So maybe I can begin with. So So if anybody has questions, kindly raise your hand in the Zoom, or just write, I have a question, then I will come back to you. So if you go to this iron and tungsten, what you did, so how did you really simulate the current injection by which you are getting the spin density? So, and is it really there is something like a critical current density, or what kind of value was it actually?
So essentially what I'm doing here, that I'm using the so we have is function on velocity operators. You just choose the velocity operator that's so you have an operator that is connected to the excitation. So the velocity operator of that tells you in which direction, on which layer you inject the current, and then you have an observable. The operator associated with the observable that can be a current, spin density, whatever you want to observe. So here I'm just applying the electric field everywhere, and I'm just applying this. I think I'm injecting the current on X here, direction X. So that would be along, let's say, yeah. So basically along this direction here. This is X, this is Y, and this is Z.
Actually, I don't know. I'm not able to see your screen. Is it shared?
Sorry for that. Maybe yeah. So basically, I'm sending a
yeah. Now we can.
So you actually have this very big Hamiltonian here. Take the derivative of it with respect to the k vector. You can have your velocity. So that's the velocity I'm using, and I'm choosing to inject, let's say, along this X direction here. So this is X, Y is transverse, and Z is perpendicular.
Okay.
Is it your question?
Yes, and if you go to the next slide.
Yeah.
So yeah, in this slide actually. So when you are making the like current injection, then you see. So I mean, and then there is another question is the x-axis or the gamma. You say the disorder. So what it is exactly?
Inverse of your momentum relaxation time. Okay, so that's this is the broadening of your wave function, of your Green's function. I'm sorry, the broadening of your Green's function, which physically is simply the inverse of your momentum reaction time. You know that based on the conductivity is proportional to the it's inversely proportional to gamma. That's just based on Drude formula. Okay, this is why you have the so if you increase the disorder, your gamma here, the broadening, then the conductivity decreases 1/gamma.
I'm sorry, Aurélien, I don't know. It's my internet or your internet. One of it's going on and off. Your voice is not very clear.
Virgin, there is no disorder. I don't know if it helps. So based on Drude formula, you know Drude formula. Time. So the momentum relaxation time is inversely proportional to the number of impurities in your system, then conductivity decreases. Okay, this is what you observe in the inset here. If you increase the number of impurities, you increase gamma, then the conductivity decreases. Okay, and we observe the same thing for the field-like torque, which is expected because the field-like torque is coming from the shift of the Fermi surface induced by the electric field. And because of this shift, because this shift is proportional also to the relaxation time, then you expect that the field-like torque will also be proportional to the amount of current you send in the system. So it's also proportional to the relaxation time. Is it?
Okay. And this, like in this study, you have taken 5 monolayer of iron. So does
Yes.
it mean that it is an in-plane magnetized system, or the anisotropy does not really matter?
So here, the anisotropy does not matter in my calculation because I know that it's a semi-realistic. This is something. It's an expression I took from Jakub Jelezny, who I have to thank for that, because I was worried that the system I'm modeling just uses parameters that are being calculated by Papa Constantopoulos, where he calculates all the S and P and D orbitals. I'm doing it not that. I inject them in my model. I want something that is more realistic. I don't want to have just a few orbitals. This is not enough. Okay. I want to have many orbitals in my system. So I do something. I try. It's not a real iron and a real tungsten, but it looks like your average transition metal heterostructures. From this point of view, I think this is fairly realistic.
Okay. All right. Thank you.
Anisotropy doesn't matter in the heat. So I don't care about anisotropy. I just put the magnetization perpendicular. You could, of course, calculate it. You could calculate the anisotropy, but because I'm only taking into a container, I won't be accurate. So it's pretty to get anisotropy with the functional model.
Okay. I think there is also some internet issues, so voice is not coming.
Sorry.
Yeah, I'm sorry. Okay, so if there are any other questions by audience, kindly ask. So I don't see any hand raised or anything written.
Yeah, can I ask a quick question?
Yeah, please, Anjan, Professor Anjan Burman, go ahead.
Yeah. Aurélien, this is Anjan Burman. Hello, can you hear me? Hello.
I think Aurélien has a little bit internet issue.
Internet issue, probably.
Yeah. So we are losing sometime we are getting.
Yeah.
Yeah. So
okay.
A quick question.
Maybe just one. Yep. Go ahead.
Yeah, I mean, is it possible to calculate the resonance frequency and damping, for example, in the 2D materials that you are dealing with, like FGT or VSE2? I mean, do you have any estimate?
So I think, no, I don't have estimate on that, but that's a good point. I have to say that for two-dimensional materials, so we have calculated several different classes of materials, and so of course you could do that. I mean, I think there are techniques that are quite specific, but where you could calculate, for example, the spin wave dispersion. You create a spin spiral and you calculate the energy using the generalized Bloch theorem, for example. So the energy dispersion using the generalized Bloch theorem, for example. So there are techniques. Damping is a little bit more tricky because you need to have a theory of damping, for example, to start with. So you could, but that's possible. I mean, you can use a Kubo formula for magnetic damping, but then you need to do what you actually need to map your Hamiltonian using Vanier interpolation,
right?
Which is a procedure. But I would say I just wanted to mention something because before doing all that, my feeling is that the difficulty with two-dimensional systems, for example, is that you have only, I would say, you just have a handful of experimental data, that tell you exactly what kind of conductivity you would have if there's any band structure, band gap, and with the lack of experimental data, it's very hard to decide density functional theory approach you should use. Whether you should use your functional, which one is better than another. And there have been zillions of publications, DFT calculations of two-dimensional materials, but to be very frank, I think we should be careful with the calculations, because I'm not completely sure that all of those publications are, or the approach that have been used in those publications are really substantiated by experimental data. So I mean, we are in a phase. We are still in the gray zone. I think we still need more experimental data and more careful analysis of the density functional approach that we should be using.
Okay. Thank you. Thank you so much.
Thank you. So any other question? Okay, so if not the case, I just want to make a small announcement that next week we will have the seminar on our regular Thursdays, and it will be 3 p.m. And next week it will be by Professor Koki Takanashi from Tohoku University Sendai in Japan. I request all of you to join. So if there are no more questions, so I think we really thank Aurélien. Aurélien, if you could stop your screen sharing, then I like to share my screen to give you a small token of appreciation. Yeah, thank you. So I share my screen. Can you see my screen?
Absolutely.
Okay, so this is a small token of appreciation from our team to you for your excellent lectures. I read it for you. The W2S seminar webinar series on spintonics, Mysore, Bhubaneswar, India, takes pleasure in presenting the plaque to Professor Aurélien Manchon from Marseille Université, CNRS, in France, in recognition and appreciation for being a very valuable speaker to give a lecture on engineering spin orbit torque in novel magnets. So I clap on behalf of everyone, and thank you so much for your excellent talk. It was really nice discussions, and I hope we can meet in person soon, either in France or most likely in India. I would be very happy to welcome you here. So with this, I also request you, if you have time, please join. Feel free to ask your group and collaborators to join the other WTS seminars. There are interesting seminars also next weeks. And yeah, it was very nice to have you. And I wish all of you good health, and see you next week on Thursday.
Thank you very much, Sumank. I really appreciate it. Thank you very much.
Take care. Bye-bye. Thank you so much. Bye.